Now that we have filtered out inorganic and organic dry matter, the only thing remaining is to disinfect the water, according to European criteria for potable water. Neither E. coli nor coliform bacteria nor enterococci are allowed to be in the water. To be more precise, in 100 milliliters of potable water there must be 0 colony-forming units of either type of the aforementioned bacteria. How do we achieve this disinfection? In our case, we will use ultraviolet light. This light, specifically ultraviolet C light, in a range between 240 and 280 nanometers wavelength, destroys the bacteria's genetic material so that they cannot proliferate. Typically, mercury vapor lamps are used to generate the desired light, since they emit light at a wavelength of 254 nanometers. Empirical studies show that at an irradiation dose of 400 joule per square meter, the amount of bacteria in the water is reduced by 99.95%. So this is the minimum dose that we have to emit to the water. The disinfection system is built up of a number of ultraviolet lamps that are arranged in a container in a way that they have a maximum possible surface. The water is directed over these lamps and exposed to the radiation. For our water treatment plant, we assume that the whole disinfection system has a volume of 1000 liters. The sum of the surface area of all lamps is assumed to be 100 square meters. That means that the layer of water illuminated by each lamp is on average only 1 centimeter thick, so that the water is exposed very well to the light. When the structure of the disinfection system now is known, we can start defining the equations necessary to simulate the disinfection process. The first thing that we have to compute is the irradiance E. It defines the power acting per area unit on the water. This means the irradiance E is defined as the power P emitted by the lamps divided by the whole area of the lamps, A. We assume that the power that the lamps emit is evenly distributed over the area. In parallel, we have to compute how long the water remains in the disinfection system. This detention period is defined as the ratio of the volume of the system and the volumetric flow rate. The resulting energy dose is computed by multiplying the irradiance with the detention period. Unit 9, Szene 5. The number of microorganisms exponentially decreases depending on the dose. How quickly this number decreases depends on the factor K. Necessary energy doses have been empirically determined in different experiments. However, the values given in literature differ. Therefore, we assume the following correlations. To reduce E. coli by 99.99%, a dose of 5.6 millijoule per square centimeter is necessary. To reduce coliform bacteria by the same amount, the necessary dose is 8 millijoule by square centimeter. And to reduce enterococci by this amount, the necessary dose is 6.2 millijoule per square centimeter. As stated above, in our system we want to achieve an irradiation dose of 400 joule per square meter. This will decrease the amount of bacteria by almost 99.99%. Since we've got a detention period of 2.5 seconds, our irradiance E is 160 watts per square meter. With our total area of 100 square meters of lamps, we need a total power of the lamps of 16 kilowatts. With these values available, we can now start implementing the final part of our model. Implement a subsystem in your model representing an ultraviolet disinfection system using the formulas presented in this unit. Model the effect of the disinfection of the 3 kinds of bacteria mentioned in the text. Update the concentration of these bacteria in the bus using their newly computed concentration. Instrument your model at will.